Okay, for today's class activity, Chapter 12, Sections 1 through 4, we'll cover these concept questions, 1, 3, 4, 5, and 6, exercise 7, 9, and 13. So go and read this section diligently and try to apply those concepts and come through this video, pausing as needed to practice on your own. Starting with concept question 1, we have this dumbbell that's made up of a big ball and a small ball, and we have these three dots. Okay. The question is, where is the center of mass? So the center of mass is the position where you could balance this thing. Okay, which means it ought to be this point right here, which is point A. Okay, because since this mass is bigger than this mass, it can't be in the middle because it wouldn't balance. It's definitely not closer to the smaller mass. It's got to be closer to the bigger mass. We'd need to know the exact masses here to be able to calculate exactly where it is, but the main idea is, where would you balance this thing? It's going to be at this point where the nearest the big mass. Okay, what about 3? Take a look at 3. Okay, this is about kinetic energy, rotational kinetic energy. So K rotational is equal to 1/2 I omega squared. Okay. And the question really is, what is I? We're told that these three disks have the same mass, but we're given different angular speeds and different radius. Okay. But what is I? So for certain shapes, we just look. We could derive it with the integration, but we also have a table that we'll reference often. Okay, so I for a disk, okay, is 1/2 the mass times the radius squared. Okay. Now don't get this half confused with this half. This half is from the definition of rotational kinetic energy. That half is the result of integrating all the masses over a disk. Okay. So that half comes from the disk. So this is the moment of inertia for a disk of mass m and of radius r. Okay, so with A, we could call this Ka because we'll reference this r and this omega. So what is Kb? All right. Well, these don't change. The mass is the same, but we're told that the radius is half as much as the original. So we have to square the 1/2 nth r. And the angular speed is twice as much as the original. So we have to square the 2 and the w. So 2 squared and the 1/2 squared cancel, and this ends up just being Ka. All right, do the same idea to Kb. Okay. Kc. So for Kc, we've got the light's coming through my window, so I have to block the light again. Kc, we have 1/2 m, and here we have twice the radius squared, but we have 1/3 the angular speed squared. So those don't cancel each other out like before, but we have an overall 2 squared, so that comes out as a 4, and 1/3 squared that comes out as a 9, and everything else is the same. That's 4/9 Ka. So this is a proportionality problem, just to be careful about what the squares and making sure that we recognize K as proportional to the square of the radius through the moment of inertia and square of omega. Okay, 4. Look at 4. Must an object be rotating to have a moment of inertia? Answer is no. It does not need to be rotating. Okay. Why not? Well, moment of inertia is rotational mass. Does something need to move to have mass? It doesn't. It's a property of the object. Okay. So I is some function, some summation of all the masses and where those masses are squared. So it just depends on how much mass there is and where that mass is distributed, not whether or not it's moving. Okay, number 5. Okay, for 5, we know that the moment of inertia of a rod about its center is 1/12 ml squared, where L is the length of the rod and m is the mass of the rod. But if we simply pivot the same rod, so same length, same mass, but pivot it about its end, the moment of inertia changes to 1/3. It grows significantly, even though it's the same rod. Why is that the case? Why can you argue that this has a bigger moment of inertia than this one? If we come back to the definition of moment of inertia, it is dependent on the mass and where the mass is distributed. Now the mass is the same everywhere, but its distribution is different. This one has mass distributed from 0 up to half L, and twice of that, because you have this much this way and this much this way. So from here to there, this piece could account for either of these two. So you say, well, this is just the other half, but the thing is, it's referencing from this point. So the first piece of this one is already at half L. The next, or the last piece, is at a total L distance away. And because this distance now is bigger and it's squared, it has a much bigger impact than just the mass alone. And so this one has a significantly larger moment of inertia because half of it is much further away than in this case. Okay, finally on 6. Okay. 6. We have two spheres. They're solid steel spheres. Okay, solid steel spheres. And one of them has twice the radius as the other. How does the moment of inertia compare? We have to think carefully about this one. How does the moment of inertia compare? Okay. Well, if we look up at our table for a solid sphere, the moment of inertia is the 2/5. Sorry, 2/5 mr squared, where m is the mass of the sphere and r is the radius of the sphere. So we might say, well, if the second sphere has twice the radius, well, we square it, so it would be a factor of 4. But we're told these are solid steel spheres. That means the density is the same. Steel has a constant density. The object doesn't have the same mass. So we have to remember that mass is density times volume, which is density times 4/3 pi r cubed for a sphere. So plugging that in for I, we end up with a 2/5 4/3 pi times the density. All that stuff is constant. The density is constant. But now we're left with an r cubed times an r squared, giving us an r to the 5th. So now if we double r, we have to take that 2 to the 5th power. And 2 to the 5th is 32. So I2 would equal 32 I1. Okay, and that again is because the mass was not held constant. It's the same material, which means density is the same. Okay, very good. Now let's move on to the exercises. Let's take a look at exercise 7. Okay. So here's a chance to work out center of mass. So we have a coordinate system here, x and y. And at the origin, we have one 200-gram mass. Okay, I'm going to call it 1. Over here, at 12 centimeters, we have a 100-gram mass. I'll call it 2. This is 10 centimeters. And then up here, straight above this 100-gram mass, we have a 300-gram mass. I'm going to call it 3, which is a distance 10 centimeters up. Sorry, this was 12 centimeters. I had my number wrong. 12 centimeters here, 10 centimeters up. And our goal is to find the center of mass of this system. Where's the center of mass relative to the origin? Okay. Now, qualitatively, where would it be? This is pretty heavy, and this is the lightest. So it's going to be closer to this one okay, somewhere up here, okay, then this one is going to be probably a little bit closer, so somewhere around there. I imagine if you had very lightweight rods connecting these three, and then you had a sheet of very lightweight plastic, rigid plastic, and were able to pivot it, you can put your finger right there and pivot these three. Okay. All right. So this is where the center of mass ought to be. Now let's calculate it. How do you calculate center of mass? Well, the big thing is you have to do it in each dimension separately. Okay. So the x center of mass is simply going to be equal to mass 1 times x1 plus mass 2 times x2 plus mass 3 times x3. And then you normalize it by the total mass. Okay. Now, this means we have to have some reference point. So that's why I said we're going to find the center of mass relative to the origin here. Where is it relative to the origin? Now, once I find where that is relative to any of these, I can move this, and I know that center of mass has the same relative position relative to these three. Okay, so in this case, mass 1 is here. That's 200 grams, but its position is 0. The distance away from the origin on the x-axis is 0. Okay, so we're left with, up here, we're left with 100 gram times the x, the position of x2 and the x is 12 centimeters. And then the 300 gram, and its x component is also 12 centimeters. Then we divide it by the total mass, well, which is 100 plus 200 plus 300. Okay, if we plug in all our numbers here, we're going to end up with 8 centimeters. Okay. Which makes kind of sense. There's 400 grams here and only 200, so it's going to be closer to this line than it would be to the origin. So 8 centimeters is a little bit further than the center of the 6 centimeters, which is the center. This is the center of mass, so it's weighted by where the mass is. So that makes sense. Okay, now we have to do it separately for y cm. Now it's the same thing, it's just instead of x's we have y's. Okay. This one's a little easier because if you rewrite this with y's, well, this one has no y component, or is y equals 0. This one does too. So the only thing that has a y component is this one. So you'd have just the 300 times 10 centimeters over the total mass of 600. And if you do that one, you end up with 5 centimeters, which is halfway up, which should make sense because vertically there is as much mass here as there is here. 300 grams, 5 centimeters this way of that line, and 300 grams, 5 centimeters that way of that line. Okay, very good. Now let's move number 9. Go ahead and take a look at that one and think about what the main idea is here. Okay, so we have a disk, okay, of radius r, mass m, and it's rotating with some angular speed omega, and we know it has a kinetic energy. Okay. My question is, what is the speed of a point on the rim? So what is that v, rim? What is the speed of a point on the rim? Well, how can we figure this one out? What do we know about this disk and its rotation? Well, first of all, we know kinetic energy is 1/2 I omega squared. Okay. We know for a disk, we can look that up for a disk, that is 1/2 m r squared. I'll use a capital R in my diagram, so I'll put a capital R there. Okay. Now we know the mass, we know the radius of this disk. Okay. And we don't know omega, but we do know k. We're not looking for omega, we're looking for v of the rim. Now omega is the angular speed which is constant for every piece of mass on this. Every piece of mass, since it's rigidly bound to each other, is moving through the same angle in the same amount of time. But the velocities, the meters per second, are different depending on how far out you are. So we could find the velocity of the rim relative to the omega by noting how far out it is, remembering that v rim would be equal to omega times the distance to the rim, which is r. In other words, omega equals v rim over r. Plugging that in, 1/2 m r squared, and we have v rim over r quantity squared. You notice we have an r squared and a 1 over r squared, so those cancel. And we're left with the 1/4 m v rim squared. Okay. We know what k is, and so we can solve for v rim. So multiply the 4 up, divide by the m, take the square root, you get 4k over m. And if you plug in your numbers, you end up with 2.45 meters per second. So here we used our knowledge of rotational kinetic energy. We used our knowledge of the moment of inertia for a solid disk. And then we used our knowledge of how the velocity at a point relates to the angular speed based on where that point is from the axis. Okay, so the rim was a specific point, and its specific distance was that far away. If we had looked at a point earlier, we'd have to know how far away it is from that point. Very good. So now let's move on to our last problem of 13. All right, now part A of 13. Well, first of all, 13 is a series of 4 spheres: a 200-gram sphere, a 100-gram sphere, a 300-gram sphere, and another 200-gram sphere. They're separated distances 10 centimeters horizontally and 8 centimeters vertically. The origin is right here at this 100-gram sphere. First question is to find the center of mass of this system. Now I'm going to let you do it because it's the same process as right here. But if you do, you'll get an answer of x cm is 25/4 centimeters, or 6.25 centimeters. Okay. Kind of makes sense, a little bit more than the 100 because there's 300 here, there's 500 here, so it should be a little bit further towards this line than this line. And then ycm is 5 centimeters. That makes sense too because there's more mass up here than there is down here, so it seems like it should be a little closer up to here. So I'll let you use this process to calculate those. But what we're going to focus on is finding the moment of inertia of this system, assuming they're all rigidly attached by very lightweight rods. If it's going to spin about this point, so spin like this about this point, an axle that went through this point vertically, so that it can spin around that point, what would be the moment of inertia? Okay, so our reference point is right here, and our moment of inertia is defined as m1 r1 squared plus m2 r2 squared plus m3 r3 squared plus m4 r4 squared. Okay. And this is just the distance from that. It's not x or y, it's just the distance from it. Okay, well, if we call this 1, this 2, this 3, and this 4, well, r1 is 0. It's at this axis. So that contributes nothing to the moment of inertia. This can be 1,000 kilograms, and it means nothing because it's at the origin. Okay. Now, R2 is this far, this 8 centimeters up. It's going to be equal to 200 grams. Well, we better convert, since we're finding moment of inertia, we better convert this. The other cases we didn't need to because they scaled the same way. So we just can report our answers in the given dimensions. The moment of inertia we ought to report in SI units. So this one, we're going to have 0.2, which is the mass of 2, times the distance it's away from this point, which is 8 centimeters. It's 8 centimeters away. So that's going to be 0.08 meters squared. Number 3 is that far away, which is along the hypotenuse of this triangle. So that's going to be 0.3 times 0.08 squared plus 0.1 squared. So one side squared plus the other side squared equals the hypotenuse. And finally, number 4, it's 0.2 kilograms, and it's 10 centimeters away. So it's going to be 0.1 squared. So if you plug in all your numbers, you could simplify this, but just plug in all your numbers, you get 0.0082 kilogram meters squared. And so this kind of gives you a feel for how big a moment of inertia would be. It's kind of hard to play with since it's so dependent on distance. Small distances make very small moments of inertia. Okay, and this is also, the masses aren't terribly big here. So it's kind of hard to get an intuition, but here's starting to build your intuition. That's the moment of inertia for an object of, hundreds of grams and tens of centimeters away. Okay, so that covers all the concepts in this reading today.